You've already talked about continuity last year when we discussed pre-calculus. And so first of all, when we think about continuity, is we think of a graph that has no breaks, no jumps, no holes. So the graph is continuous. So when I think about this with my pen or my pencil, a graph that is continuous is a graph that I keep drawing and I have no breaks. So I never pick up this pen or this pencil. It just keeps going and going and going. Okay, and so the definition of continuity, it says a function f is continuous at c if the following three conditions are met. So first of all, f of c is defined. So this basically means that you have a y value. Okay, when it says f of c is defined, that means you have a y value. The limit exists. Okay, and the limit as x approaches c of f of x equals f of c. Okay, and we'll talk about those limit meanings shortly, but then continuity on an open interval. If you look at this definition, it says a function is continuous on an open interval if it is continuous at each point in the interval. A function that is continuous on the entire real line is everywhere continuous. Okay? So when we think about continuous, the opposite of continuous is discontinuous. And so here are three examples of discontinuities that we have up here. Okay, the first one, if you look at that, it's not defined, so that fails that first characteristic when we discuss continuity. Okay, there's no y value. The second one, it says the limit of f of x as x approaches c does not exist. The reason it doesn't exist is because it approaches a different value here as it does here. So remember that the limit from the left does not equal the limit from the right. And then here, the limit as x approaches c of f of x does not equal f of c. So notice here we've got a gap. All right, so then let's talk about these, because if you remember back to pre-calculus, we classified discontinuities as either removable or non-removable. And remember, we had a nifty little way to classify them. Okay, we're going to take our pen, and if there is a way that I can put one dot in this graph so that the discontinuity is gone, that's called removable. So could I put a dot on this first graph? So if I put a dot right here, would you agree that there are no breaks in the graph? I could walk along that graph and not fall. Yeah, so this is what we call a removable discontinuity. Okay, that is a removable discontinuity because you have removed it with your pen. Let's look at the next one. Can I put one dot on the graph, one dot, and remove that discontinuity? If I put a dot right here, understand that I'm still going to have a break in the graph. I'm still going to have a fall as I go over here. You're going to fall or you're going to have a jump. And so as a result, this is a non-removable discontinuity. Okay? This is a non-removable discontinuity. What about this next one? What would that be classified as? See if I put a dot here. Is there a way you could still walk along this graph without falling? So this is a removable. That's that y value. Another place you will see non-removable discontinuities is with asymptotes. Okay, asymptotes mean non-removable. So what we're going to go ahead and do is we're going to go ahead and look at some examples. So I want you to go ahead and graph the following on your graphing calculator. F of x equals 1 over x. Okay, f of x equals 1 over x. And so now graph this on your calculator, and we're going to go ahead and talk about the continuity of this graph. Y equals, yep. Graph y equals 1 divided by x. This is the first example we're looking at. So, okay. So if you graph 1 divided by x, you should get something that looks like this. Right? Is this graph continuous? Yes or no? Then you do zoom Z standard. Okay, so this graph is not continuous. Where is it not continuous at? Yep, so x equals what? 0. Now I need to classify what kind of discontinuity is at 0. Okay, so right here is where my discontinuity is. Can I put a dot right there and remove that discontinuity? So this is a non-removable. Yep. And we'll add some more stuff to it. Okay, just a second. I want you to graph this one and then I'll go figure out what's wrong with the calculator. I want you to graph this. F of x equals x squared minus 1 over x minus 1. Okay, now what do you think about this graph? I want you to go to zoom and I want you to go to Z decimal right now. Where's it discontinuous at?
2.
X value. Non-removable or removable? Removable because I can take one dot and remove that discontinuity. Now real quick, that Z decimal shrinks the window down a little bit. Now that's what I'm going to talk about. Is there a way that I could look at this graph up here, boom, and look at this graph here and say there's going to be a discontinuity without even graphing?
I'm sure you'll tell us where.
Each of these is fractions, correct?
Yeah.
And what can't you have in a fraction? 0 where? In the denominator. So if I look here, the denominator equals 0. Ah, look at our discontinuity. What value here makes this 0? Ah, there's where your discontinuity was. So discontinuities basically occur when your denominator equals 0.
How do you get x minus 1 over 0?
Because remember what I just said, okay? You can't have a 0 in the denominator of a fraction, correct? It's undefined. Whenever you try to divide by 0, it's undefined. And so what we can do now is, instead of just relying solely on our graphing calculator to tell us stuff, because sometimes it doesn't tell us the right things, we just saw that in that example, we can look at it algebraically and say, oh, there's going to be a discontinuity here. So let's go ahead and look at this one right here. I'm just going to pick another one. Let's do f of x equals x squared minus 4x plus 4. Okay, before you even graph it, let's analyze what we know about this graph. What is it going to be? A what? Parabola. Is it going to open up or down? Up, because it's a smile. So let's talk about what we know about parabolas. Are parabolas continuous? Are there any discontinuities here? No, so there are no discontinuities. So it's continuous everywhere. So it's one of those, the graphing calculator is great and I want you to use it, but I also want you to use your mind a little bit and not analyze and not rely solely on that. All quadratics parabolas? Yes, they are. What the sign of this is. If this is a positive, remember it's like a smile. If it's a negative, it's a frown. And it goes upside down. Okay? So far so good? Let's talk about one more. F of x equals the square root of 1 minus x squared.
Is that a 1 minus x squared?
Yep.
Oh,
Nope, 1 minus
I
x
thought it was
squared.
like a bracket.
Nope. 1 minus x squared. What's the graph look like? Half circle? Okay. Do I include the points 1 and negative 1? Yep. How do you know? You plug it in. 1 minus 1, square root of 0. Yes, you can take the square root of 0. Okay, so right here. Okay, so continuity. What can you tell me? It's not continuous everywhere, but where is it continuous? Okay, so let's write that using interval notation. Yep, bracket, negative 1, positive 1. And there you go. Not too bad. Now this isn't the entire section, but this is all we're going to do today. And then we'll talk more about the intermediate value theorem tomorrow. But I want you to go ahead and get started. And so this is what I want you to do. Okay, I'll go ahead and start a new slide here. I want you to go to pages 78 and 79. I want you to go ahead and do 1 through 6. And then I want you to do 33 through 42. Okay. Now real quick, let's go ahead and get started on number 1 because that's actually going to be a segue into what we do tomorrow. So on number 1 it says use the graph to determine the limit and discuss the continuity of the function. Okay, and so, you know what, I'm just going to wait. I just want you to do 33 through 42 for right now. Okay, so do 33 through 42 and that'll be good. We'll add 1 through 6 tomorrow.